Hello, everyone. Welcome to the last session of the day. I hope you still have some energy for Adam, founder of CodeScene, for a very interesting topic on how technical problems cause organizational friction. Please give him a big round of applause. The stage is yours.
So, good afternoon, everyone. Having a good conference? Yes. Great to hear that. So today, we are going to cover 5 socio-technical smells as well as their resolution. And the basic idea in this presentation is that organizational problems very often have technical root causes. And by mitigating those technical root causes, we can solve seemingly hard organizational problems. And I'd like us to start by taking a step back and look at why software is so hard. So a little bit of challenge for you here. If you look at this piece of code, how many of you can quickly tell me what this code does? Not so many. How many can tell me if this code is correct? I also don't have any idea whatsoever, and I've been coding for 35 years now, right? What I want to point out that this is 19 lines of code. A modern software system has millions of lines of code that looks just like that, right? So I like to claim that the modern software system simply outscales the cognitive capabilities of us as humans. And it becomes even more challenging once we add multiple developers and multiple teams on top of our technical solutions. So let's start with that in the back of our head. Let's start to explore the first socio-technical smell, which is called the overcrowded system. And this is something that I promise all of you have experienced at some point. And I'd like to introduce this code smell by giving you a book recommendation. This is the best book that hasn't been written yet. This book has the lovely title, Death March, The Art of Doing Half the Work in Twice the Time, with the subtitle, Fix Your Visual Thinking by Adding More People. Has anyone seen that happen in real life? Yeah. So I'd like to share a story with you. This is something that happened to me many years ago. At that time, I worked for a product company. And this company, they had a project that had been going on for a couple of years. During those years, they had missed deadline after deadline. And now finally, it started to become critical because that project had to ship in 3 months. If they don't ship, the company would be subjected to quite some heavy financial fines. So it started to become really, really urgent. And me and our colleague, we were called into management, and management asked us that, do you think there's any way of saving this project? Can we do something to ship in 3 months? And we promised that, okay, we're going to get back and have a look at it and see what we can do. So we went back and had a look at that project. We looked at the code, we talked to the team, and we came back to management. And we told them that, you know, we took a look at the problem and that we actually have both good and bad news. The good news are that we're confident that we can ship this in 3 months. And I mean, you can feel the tension in the room kind of just dropped. And everyone was like, yeah, but that's absolutely amazing news. Thank you very much. So what were those bad news? I said, the bad news are that you're not going to like what we're going to do. Because what we planned to do was to take that software that had been developed over 2 years and throw it all out and rewrite it within that 3-month window. And it was quite a hard sale. But we kind of motivated to management why we want to do this, what our reasoning was, and why we were confident that we could pull it off. And for reasons that still surprise me to this day, they actually gave us the go-ahead with that. What they also asked us was that, okay, how many additional people do you need? Because there were currently 25 people on the project, right? Because with each missed deadline, a couple of other people have been brought on. So there were 25 people. How many more would we need? And I said, 5 people. Said that, okay, that's not too bad. You want to go from 25 to 30 people? I said, no. We want to have 5 people in total. And again, somehow we got the go-ahead for that. The reason I was confident that we could pull this off with just 5 people is because I had been reading this wonderful book called The Mythical Man Month. So how many of you have read this book before? So like a couple of you, maybe 10, 20%. For the rest of you, put it on your wish list. It's a brilliant book. And today, it's probably best known for what we call Brooks' Law. And that's the fundamental fact that adding people to a late software project makes it even later. And I have tried to make a visualization that explains the dynamics behind Brooks' law. And the idea here is quite simple. On the x-axis, you have the number of people you can add to that project. And on the y-axis, you have the number of months until completion. And you see that to a certain degree, you can add a couple of people, maybe 3, 4 people, and you get a shorter completion date, so you can ship faster. That's good. But then at some point, we see there is some kind of turning point, right? And beyond that point, each additional individual that we add leads to a longer completion time, right? So we would ship late. The reason this is happening, Fred Brooks, the author, claims, is because with each individual that we add, we get a fixed number of hours extra available, right? In Sweden, it's typical like 40 hours a week, right? So we get those extra hours that we can do work with. But the thing is that those hours increase linearly, while the coordination costs of each individual expand much, much more rapidly. So at some point, all those extra hours that we get are going to get consumed by additional coordination and then some. So actually, at some point, each individual that we add is going to be a net loss to the project. And once this is happening, there's really just 2 things you can do to rescue a project like that. The first option is that you simply shrink the organization to fit the modularity of the work that's being done. And this is what we choose to do on that project I just told you about, right? But there is another option too. And the second option is much, much harder, but what you can also do is that you can redesign and re-architect so that the system can accommodate more work being done in parallel. Typically by increasing the modular boundaries of the system so that you can have more teams working independently in parallel. Now, before I continue, that project I told you about that we were supposed to rewrite and complete in 3 months, how many of you think that we actually pulled that off? So I think it's a majority. And of course, it's easy, otherwise I wouldn't be telling you about it, right? But actually, we didn't need 3 months. We actually shipped 2 weeks early. So we took what had been done over 2 years with 25 people, shipped it in 2.5 months with 5 people. And the reason I'm telling you this is because it kind of indicates the amount of waste that we create when we fail to pay attention to our socio-technical fit, when we fall victim to Brooks' law. And I like to think there's a reason this is happening, because Brooks' law is from a book written in 1975, right? And it describes a software project from 1960. So why are we keep repeating these age-old mistakes? I think I know the answer to that, and I want to test it on you. So please, have a look at this code. Looks great, doesn't it? Who can tell me if this code is a major coordination bottleneck for our 5 different feature teams? Or if all that code is written by just one developer so that we might have a key person dependency? No one. Because we just cannot tell. And this is the reason, or this is something I like to call the grand tragedy of software design, that we, the people who build the code, we're actually invisible in the code itself. A piece of code doesn't reveal anything about its socio-technical fit, and that's why it's so easy to overlook these typical mistakes. So how can we bring visibility to the people side of code? This is a topic I've been exploring over the past 15 years in my various books. And in Software Design X-Rays, I introduced the concept of behavioral code analysis. So how many are familiar with behavioral code analysis? Anyone heard about it before? So maybe 5–10% of you? Cool. So I want to give you a quick summary and overview of what it is. So the core idea in our behavioral code analysis is that the code itself, how it looks, is important. It really is. But it's even more important to understand how we, as an organization, work with the code we're building. And throughout this session, we're going to meet a couple of different behavioral code analysis techniques using slightly different data. And we're going to apply behavioral code analysis to the next socio-technical smell, which is called coordination bottlenecks in code. So what is this all about? Well, we already looked at a piece of code. Let's now look at our software architecture. So would this look familiar to you? I think so. This is like my generic architecture, right? This is what like 90% of all business software out there looks like. We have a couple of components, perhaps there are services, they interact with each other. We have a bunch of databases, data sources, and then of course we have various clients, different mobile clients, we might have a web client, and of course we might communicate with other systems over mechanisms like REST, right? So far, all is good. However, what I like to claim is that using all these different technologies and having a system, a typical business application is somewhere around 1 million to 1.5 million lines of code. There's simply no way you can fit a system like that into a human head. So already here, it's virtually impossible for human brain to grasp all the details. The thing is, we don't. What we do as humans when we reason about a complex system like this is that we use something called mental models. So when you think about a piece of code, very few of us have a literal representation of the source code in our head. What we have instead is a simplified mental model that fits our head so that we can reason about the problem and the solution. Now, I like to claim that if we think back to this overcrowded system effect, that the more developers we have working on the same parts of the code, the same files, the same subsystem, the harder it is to maintain those stable mental models. So social factors will influence how we perceive a code base. And I'd like to give you an example on that. So let's say that you wrote a piece of code yourself today. So you have a perfect mental model of it. When you look at that code 3 days later, 5 other developers have been working on it in the meantime. So now when you come back, the code looks completely different. And that means you either have to kind of spend time reading the code, understanding what happened to it, so you can rebuild your mental model, which is really time consuming, right? If that is something that continues, you're going to be in a constant onboarding mode. Or you have to take the risk and make changes to that code based on an outdated mental model. So in an overcrowded system, you also tend to have very strong coordination effects in the code. So if we have an important socio-technical smell like that, how can we shine a light on it? The first thing we need to do here is to collect some evidence that points us in the right direction. Do we have this problem or not? And in this case, we're going to turn an eye towards our Git logs. So this is a small piece of a Git log. And we can see here that a Git log actually reveals something about the socio-technical context. Because I can see that David has worked on a particular file and Steven worked on the same file within a week's time, right? So what I can do now is that I can calculate some statistics from the Git data. And I can put together a table like this. This table, by the way, is built by, it's one of my old open source tools. It's called CodeMath. And it's capable of generating tables like this. So I can quickly see that, okay, we seem to have a coordination bottleneck in our build system. You see this Python file, builder.py, right? There have been 13 authors working on it. I think this data is from the past 3 months. So past 3 months, 13 people working on it, right? So it does seem quite crowded. And this might be a good start. However, in a larger system, it's really, really hard to see patterns in tabular data like that. So what I tend to do for larger systems, for real-world systems, is that I tend to visualize them. In general, I'm a big fan of visualizations because visualizations, they tap into one of the most powerful pattern detectors that we have in the known universe, the human brain. And what you see here is a visualization of coordination bottlenecks in a code base called Folly. So Folly is a modern C++ library from Facebook. It's really nothing special about it. I'm going to pick a bunch of different code bases as we go along. But what's so interesting here is that we can quickly point out the coordination bottlenecks in code. And I want to walk you through this visualization so you know what you're looking at. The first thing I want you to pay attention to are these large circles. So these large circles, they represent top-level folders in the Folly repository. So if this is would be one of your code bases, you would recognize the names of those folders as important subsystems or like high-level components. And we see that inside those large circles, each file is visualized as a circle too, a colored circle. And you might see that those circles, they have different size. Some are quite big, others a little bit smaller. That's because the size of the circle reflects the number of lines of code, so that we know visually how big a potential problem is. The important thing here is the color. You see that some are much more red than others. And color is used to indicate author density. So the more people we have working on the same parts of the code, the more red it becomes. Right? You're with me? Good. So if I look at Folly, what part looks interesting? Well, the part to the left, which is about asynchronous communication, really stands out. So let's zoom in on that part. And when I do that, I see that these files, they have 58 authors working on them, and this data was collected over the past year. So 58 different people over the past year. It basically means that each week a new developer goes into that code. Who thinks it's super easy to maintain a stable mental model in that code? It's only me that's the optimist, right? Of course, it's impossible. It's virtually impossible. So what do you do now? Now we can clearly point to a specific problem. And it seems to be an organizational problem, right? Because we have 58 people in the code. But I like to claim that very often this has a technical explanation. So when I find something surprising like this, I always look at the code. So let's bring up this major coordination bottleneck and have a look at it. I have a lot of respect for the fact that it's late in the afternoon and reading C++ code might not be everyone's idea for a great evening. So rest assured that you don't need to look at the details here. What I want you to do is just kind of look at the overall patterns, because I want to share some heuristics I use when I investigate code like that. The first thing I look for is a pattern like this. Do you see that? There's an if statement indicating a special case and then a very lengthy comment. 99% of the cases, that's a sure sign that this is a separate responsibility that ideally shouldn't be in that function at all, right? Maybe it should be extracted into a separate function or maybe even a separate class so we can capture that responsibility. If I continue to read the code, I see that there are various chunks of deep nested logic sprinkled throughout the code like this. This is something I call the bumpy road code smell, right? You know, your code looks like a bumpy road, and just like driving on a bumpy road is going to slow down your driving speed, reading this kind of code is going to slow down your code comprehension speed. So this is also something we want to avoid. And if we combine these two findings with the fact that what you see here is only a small snippet of a class that has several thousand lines of code and more than 100 functions that look just like that, then I think it's a fair assumption to claim that what we have here is a God class, right? So who has heard about the God class design smell? It's like 1/3 of you maybe. Good. So the God class, the definition I use is that the God class is a design smell that we use to describe modules like that compulsively collect responsibilities and contain complex logic. And the reason I'm interested in God classes is because they have a lot of impact on the organizational dynamics of the people who work on the code. In fact, God classes, they are really the traffic jams of the software world. And what I mean by that is that a God class, they're going to implement so many responsibilities, so many business rules. So no matter what team you work on, no matter what area you work on, you're going to end up in the God class and have to make changes to it. That's why they become so congested. So God classes basically force developers working on different features into the same parts of the code. And that's a very good explanation for why we have 58 people in the same file. So how do we mitigate this? What do we do when we have a problem like that? Well, in this case, it's very much about trying to introduce cohesion into the design, because cohesion is a very fundamental property for scaling the people side of code. And I'm going to try to explain what I mean by that. And I could have picked any research reference because there's a lot of research paper that suggests that there's a very strong alignment between a highly cohesive design, that is where we have each responsibility clearly isolated, and the coordination needs of the organization. So I wanted to demonstrate this on a different code base. So this time I picked on a golden oldie, Hibernate. So I think some of you might have come across Hibernate, an object relational mapper implemented in Java. And I have identified a coordination bottleneck here called abstract entity persister. But please don't let the name fool you, because let me assure you there's nothing abstract about this class at all. In fact, that class contains 5,000 lines of code and 380 methods, right? And you don't really need many software measurements. Once you know you have 380 measures in a single class, methods, you kind of know that this is going to be a God class. So what do you do when you have this problem? What I tend to do is I use a heuristic. So I look at the names of the different methods. And what I try to do now is that I tend to group them by responsibility. So I take what I know about the problem domain and I try to group the methods accordingly. And then I use some very simple refactorings like extract class and try to put a good descriptive name on each extracted method block. So that means I could pretty quickly regroup the methods in the following classes. Maybe a proxy class, a lifecycle class, and a class to capture natural identities. The thing is, by doing that, I haven't really changed the code. I've only restructured it. But I like to think that the socio-technical context that results from that is fundamentally different. Because what I have done now, by introducing more cohesion into the design, is that we have created a situation where we have more natural boundaries for the developers. So let's say that I'm busy working on a feature for the proxy. Now I have one natural place to work, right, where I can safely modify the code. You might work on the lifecycle. You have a different place, right? There's no reason for our changes to different parts of the domain to collide in the code. So this is the kind of power that highly cohesive designs enable. But so far, we've really only looked at coordination inside the same class. A potentially even more interesting coordination cost comes from the interactions between various classes and packages. So I would like us to take a little bit of time and talk about dependencies. Because one thing I learned is that not all dependencies are equal. And in fact, when we as developers tend to talk about dependencies, what we often talk about are static dependencies, you know, the ones we can actually see in the code. Class A uses class B, right? But what I have found over the years, the hard way, is that if we restrict ourselves to static dependencies, then two things will happen. First of all, we might miss the most interesting dependencies, which tend to be logical, not necessarily physical and evident in the code. And second, our data isn't really going to be actionable because even a non-trivial system has a ton of dependencies. Some of them are expected, we actually want them, and that might be things like, you know, we use something from the standard library, whereas other dependencies might be highly problematic. So I like to think that the main challenge here is to draw a distinction between the good dependencies, the ones we want, and the bad problematic dependencies. So how can we do that? Well, let's try to return to cohesion and see if cohesion can give us some guidance. This time I want us to look at cohesion at the package level. So if you have a highly cohesive design, you would expect your software to look a little bit like this. We have two packages. We can see that there is a dependency between them, but there's really only one, right? So one package might use the other one. So it seems that the dependencies between packages are highly controlled. We also see that the elements inside a package depend on each other. And that's probably a good thing because it kind of indicates that these elements belong together. What we can do now is we can contrast this to a design with low cohesion, which might look much more like this, right? So we kind of see that we have these absolutely wild dependencies between the packages, right? And we even see that in a low cohesion design, the dependencies inside a package tend to be pretty tight as well. And we see that these dependencies, they kind of ripple over modular boundaries. Now, wouldn't it be good if we could quickly categorize our dependencies as being either on the good side of things, the expected dependencies, versus the low cohesion dependencies? Let me show you a behavioral code analysis technique that helps you in that direction. And this technique is based on a very fundamental fact. It's that fact that source code changes for a reason. I mean, we don't just change code at random. If we do, then we have larger problems than cohesion, I promise you. So code changes for a reason. And there are patterns to our changes. So what if we can evaluate how well our actual modifications to the source code matches our desired patterns, what we have set out to do with the architecture, right? The way you do that is by using something called change coupling. So how many are familiar with the concept of change coupling? So not so many of you, a few. Very good. I have something new for you. That's always good, isn't it? Cool. So let's see what this thing is. Change coupling is something that cannot be calculated from source code. It can really only be calculated from the evolution of the code, which in this case means Git data. So again, we pull up a Git log, but now we look at something else. This time, what we're trying to do is to identify clusters of files that tend to be changed over and over again as part of the same commits. And I wanted to visualize this for you, so I brought up a simple example here. So let's say we have this system with just 4 different classes or modules. And the first time we make a commit here, maybe we add a new feature, we change the login module and the chess module together. The second time we make a commit, we're modifying something completely different. The third time we make a change, maybe we do a bug fix, we modify the login module and the chess module together again. So now, if this is a trend that continues, there has to be some kind of relationship, some kind of dependency between the login module and the chess module, right? Because they kind of keep co-evolving like this. That indicates change coupling. They are coupled in change. And again, with change coupling, if we visualize it, then we can start to reason about package cohesion, and we're soon going to see how that relates to the organizational side of code. So far in the talk, we have been torturing our C++ code base and the Java code base. So I think it's only fair that we turn our eyes towards C#, right? So what you see here on the screen is ASP.NET Core, a framework developed by Microsoft. And ASP.NET Core is basically a framework for writing dynamic web applications. And what you see here in this visualization, if I click on it, I will see that once I hover over an element, I can see the change coupling light up. In this case, I'm hovering over a package called integration tests. So this is test code. And what I see here is that there seems to be pretty tight dependencies inside that package, right? And that's probably something I would like to understand a little bit better and make sure that that's really expected coupling and not just some copy-pasted test code, right? I want to make sure about that. But if I look at it as a package level, I see that all dependencies are inside the same package, right? So that package at least seems to be cohesive. There's nothing unexpected going out from that package. So this is probably a pattern I could live with. I want you to contrast that to this second type of dependencies. So this is, again, test code. This is an end-to-end test called a razor page test. And what this visualization indicates is that when I make changes to razor page test, I have predictable modifications in 4 other packages too. That looks pretty expensive, doesn't it? Right? So this second case of coupling seems much more problematic. And in general, when you analyze change coupling on your code, you will see 3 different types of patterns. And I want to go through them because a really important thing with change coupling is that change coupling in itself is neither good nor bad. Change coupling really just describes what the system looks like and how it evolves. So as such, we always need to contextualize our findings when we interpret them. And I want to show you these 3 patterns, and then I think you will see what I mean by that. So let's look at the first typical scenario you can find when you analyze change coupling. So what we have here is on desired change pattern. We have a piece of application code that changes together with its unit test. That's a good thing, isn't it? It typically signals that we're keeping our unit tests alive. So this is actually good coupling. That's the type of coupling we want to have. What about the next one? This is a little bit more tricky. So here I see that it seems to be a model view controller pattern, right? So I see that when I modify some of the views, I have predictable modifications in the models and the controllers too. What about that? Is that good or bad? Actually, I would like to claim that it's both, right? It's good in the sense that this is what I would expect from a model view controller. This is more or less what the pattern mandates, right? So it's a predictable modification. On the other hand, it looks kind of expensive that each time I modify something here, I have to traverse the 2 different parts too. So maybe this is something we can use as a team to discuss that design and see, is that really helping and supporting us, or is there a simpler pattern for what we want to do? but still might be acceptable. Let's look at a more dramatic pattern. The next one I'm going to show you is Telegram for Android. This is what the change coupling looks like in a God class. So there's a God class called chat activity. I'm not a Telegram user, but I would guess that chat is a pretty central concept, right? Central domain concept. And this is a pretty big class. But what you also see here is that it's coupled in change to 25, 30 other classes. And that is the very nature of God classes. They centralize the behavior so much so that everything depends upon them, right? So this is a design that's going to be really, really hard to work with. So when you evaluate your change patterns and your change coupling, please keep this principle in the back of your head, that change coupling is problematic when it violates your architectural principles. And the reason I say this is because violating your own architectural principles is very likely to lead to a surprise to a developer coming after you. And trust me on this one, that surprise is really one of the most expensive things you can ever put into a software architecture. So, now that we've explored dependencies, I want us to look at a particular type of dependencies, the ones that cross team boundaries. And to do that, we need to know a little bit about the teams working on the code. How can we get insights into the teams? Now we can no longer use the raw Git data because Git data doesn't know anything about your team context. So what I tend to do when I'm analyzing team is that I tend to take individuals and then map them to their team. So maybe Jennifer works on the framework team, David is on the scaling team, and Mr. Falcon is also on the framework team, and so on, right? So by doing this, I can do the same type of analysis we did before, right? When we figured out the coordination needs in code, but now from the team context. And I want to show you an example on what that can look like on a real code base. So what you see here is the same type of visualization, but now each team have their own color, and the team that has written most of the code, and here I never look back more than a month, so the team that has written most of the code over the past month, they kind of get their color on that part of the code. So that makes it possible to visualize the operational boundaries of the team. So I can see where the query team has worked, where the REPL team has worked, and so on. So now I can find patterns to the teams. This is a pretty good start because now I know where each team works. What I can do now is that I can intersect this with the change coupling information and see, okay, is there any change coupling that crosses team boundaries? And the reason I think this is so important is because modularity alone, I talked a lot about high cohesion and the need to increase modularity, but modularity alone doesn't guarantee a successful software architecture. Because I've seen so many systems, particularly now in the past decade, with the rising popularity of microservices, where the system is very modular in the sense that there are lots of different services. But if we get the service boundaries wrong, then we might create super strong coupling. And that can impact the different teams that own the microservices. So if I have a change coupling that goes like this, what I really have to ask myself is, what if those modules that are coupled, services and module, what if they are owned by separate teams? In that case, I like to claim that our main problem is not necessarily a dependency between code, but a dependency between people. And that tends to lead to very long lead times when trying to ship new stuff. In particular, this situation has a special name. It's known as shotgun surgery. Has anyone heard that before? So shotgun surgery simply means that, I want to tweak a simple business capability, but now I end up modifying 15 different files in 3 different services. And if you have a shotgun surgery situation, it's going to be virtually impossible to add any kind of sense-making team structure on top of it, because no matter what you do, those teams will be tightly coupled due to the change dependencies. So my recommendation, as before, is to always align your software architecture with the problem domain. Because if you do that, then you also tend to create natural team boundaries, because tasks tend to be parallelizable at the domain level. So, now that we have discussed dependencies in a team context, I'd like us to have a look at a related topic. I'd like us to talk about knowledge and code quality. And the reason I want to focus on this as an important socio-technical smell is because getting the people side of code wrong has killed more projects than even Visual Basic. So let me share another story with you. This is something that happened to me maybe 5-6 years ago, some couple of years before the pandemic. So as part of my day job at CodeScene, I also go to visit different organizations, help them out managing their technical debt, that kind of stuff. And in this particular case, I did a workshop for a large company in Germany. So I went down there and sat down with one of the teams, and they had 2 code bases. We analyzed their code bases, looked for technical debt, saw how we can prioritize it, discussed it, and there were some findings for sure. But overall, it seemed manageable, right? Some job, but manageable. But then towards the end of the workshop, someone told me that, you know what? We actually have a 3rd code base as well. So I said, okay, yeah, but we still have a little bit of time, so should we look at code base number 3 too? And now everyone started to give each other funny looks. And I was like, I'm clearly missing out on something here. So I had to ask them, so what's about code base number 3? And suddenly someone spoke up and told me that, we don't really need to analyze code base number 3 because we know that it's a mess. Yeah, I think that's the technical term, a mess. So I said, okay, that's super interesting. Now we definitely have to look at it, right? So we did. And, we had these various code health metrics. We can measure how healthy the code is, how much technical debt there is. And we did that on code base number 3. And guess what? There was objectively no measurable difference between the first 2 code bases and the 3rd one that was claimed to be a mess. And the team at first was a little bit skeptical, right? So we actually had to spend some time pulling up different code samples, compare and look. And after 10 minutes, everyone was kind of on board that, yeah, there's actually no worse quality in code base number 3. So what happened? Well, what happened, and this is something that completely changed how I view software development, is that the team told me that code base number 3 had a different history. Code base number 3 had been developed by a completely different part of the organization by a team that has since been disbanded. And this team in Germany had simply inherited that code. So it wasn't that the code was more complicated. It was just that they weren't familiar with the code. And I think this is so important because it's very easy to confuse a lack of familiarity for complexity. And if we do, we will solve the wrong problem. We might spend time refactoring something or rewriting something that doesn't need to be rewritten. What this team would have needed would be allocated time for learning and a proper onboarding. That would have solved the onboarding problem. So after learning that, I kind of figured out that there is some interesting link here between code quality, how we perceive it, and familiarity, how familiar we as a team are with the code. And some of you might be aware of this study that me and my research colleague, Dr. Marcus Borg, published 2 years ago. It's called Code Red. And what we wanted to do here was to connect code quality to a business impact. And what you see here is one graph from that study. So what you have on the y-axis are 3 different code health categories. How healthy is your code? How easy it is for you as a developer to understand it? And on the y-axis, you have the time it takes to add a new feature or fix a bug, depending on how healthy your code is. And what you see there is that red code, that is highly problematic code, complex code, low code quality, high technical debt, making a bug fix or adding a feature to red code can take 10 times as long as changes to green code, right? Even if the changes themselves are of corresponding complexity. So there's a massive, massive overhead to us developers when working with unhealthy code. And when we did this study, we saw a large variation in red code. So one of the things we kind of figured out is that there might be a people dimension to this as well. In particular, we wanted to look at onboarding. How does the code health impact our onboarding time? More specifically, if you want to make changes to a highly complex piece of code, does it matter which programmer that makes that fix? We've probably all experienced that, right? We have this, you stand in that product meeting, and someone says that, yeah, we need to add this particular feature to that system over here, system X. And everyone looks at each other and say that, yeah, the only person who understands that system is person Y. And person Y just went on vacation for 3 weeks, right? And no one dares to touch this code. Ever seen that? That's red code with the key person dependency. And we wanted to shine a light on this. So we published another study last year where we looked at what's the difference between me as a developer who has written all that code, how quickly can I make a change to it, versus a newcomer that hasn't looked at that code before. And what we found was really, really interesting. We found that for yellow code, that's code that's already has technical depth, but it's not a complete disaster yet, but we need to be careful. Already there, it takes me as a newcomer 46% longer if I want to make a small change to it, right? A small bug fix, like a one-line bug fix. I'm going to need 46% longer than the person who wrote that code and is familiar with it, has a mental model. If it's a larger change, like adding a new feature, I'm going to need twice as long. So this is basically onboarding overhead. And what's so interesting is that for green, healthy code that's easy to understand, there's no measurable difference between the person who wrote the code and someone who hasn't worked in the code before. So green code seems to have a much, much smoother onboarding curve, right? Onboarding in green code seems to be virtually free from a technical perspective. And this kind of brings me to a factor that you might know as the bus factor or the track factor. Or maybe even my personal favorite, the lottery factor. Have you heard those terms before? They're basically the same, different terms for the same thing. The track factor refers to how many developers can leave our team before the code becomes unmaintainable, right? And the lower the track factor, the bigger a problem we have. And I wanted to visualize the track factor for you, what it looks like. And I was looking for good case studies, and I decided to do this on the React code base, React from Facebook. So how many of you are using React today to build your applications? It's like maybe 10% of you. How many of you have looked under the hood at the code? A couple of you, maybe. Good. So let's take a different look at React here. And again, there's nothing special about React. The reason I picked this is because according to GitHub, React has more than 1,500 contributors. So what do you think the track factor could be in React with 1,500 contributors? How many developers could leave before we lose detailed knowledge of, let's say, 50% of the code? 500? 1? Wow. That was actually a little bit overly pessimistic. The answer is 2. The track factor in React is 2 people. Everything that's indicated in red, that's the parts of the code where you lose detailed knowledge if the wrong 2 people leave the project. Should I be worried? I probably should. Just to show you that this is no fluke, and also to show you that I'm not doing this just to point fun at React, let's look at its competing framework, Vue.js. The track factor in Vue is actually half of the one in React, 1 person. So if 1 person, the founder of that project, leaves, you're going to lose detailed knowledge of 80% of the code base. Which one would you be the most worried about? What do you think, React or Vue? I would be a bit more worried about React. Why is that? Because this familiarity dimension track factor is only one part of it. Remember a study I just told you about. If our code is healthy and high quality, we can more easily onboard new people, right? And so there's a different dimension here. And you see that as indicated by these dashed borders around certain files. That indicates that you have a track factor problem in complex code, right? And we see that there are several of those in React. That's this whole cluster of complex code with low track factor. So that's the part of the code where it's going to be extremely expensive and hard to onboard a new developer. In Vue.js, the code looks much cleaner, right? There are much fewer instances of these problematic parts. I can really only see one. On the other hand, it's in a package called compiler. I don't know anything about Vue, but a compiler might be important. So what I wanted to share with you now is that code quality issues tend to amplify organizational problems like the track factor. And my recommendation is that when you think about paying down technical debt, then let community smells be a driver for refactoring. Specifically, you want to prioritize improvements to unhealthy code with a low track factor. So if these were my code bases, like I'm responsible for this, I'm the tech lead on this or something, what I would do then is I would probably take the persons working on that part of the code, pair them up with another developer, have them refactor that code together. Because not only am I going to distribute knowledge in the process, I'm also going to mitigate a potential future offboarding risk by having healthier code. So with that covered, we have come to the end of our socio-technical tour. And what I wanted to show you today is that when we do software design, we also do social design. And what I find interesting is that the socio-technical fit benefits the people organization. And we have seen that seemingly hard organizational problems can be reduced via technical improvements. So we have seen examples on how we can simplify and make onboarding more effortless and cheaper by flattening the learning curve. We've also seen how these same techniques can help us reduce key person risk, right, and kind of step out of the truck's way. And we've also discussed how we can decouple teams via highly cohesive design, which in turn let us minimize defects and actually improve team morale. It's going to be more fun to work on a system with a good socio-technical fit. And if you want to read more on this, the good news are that all these claims I've made, because they do sound like strong statements, all of them are supported by research. So I wanted to give you the references here, in case you want to read up on it. The tool I've been using for doing the analysis and the visualizations is CodeScene. We're here at the conference. We love JFocus. We're happy to sponsor it. So if you want to learn more about the tool, please visit my colleagues down in the booth. I'll be hanging around there as well. Be happy to answer any questions you have. And of course, you can try it out for free on your own code if you want to see what your socio-technical fit is. Finally, since it's a Tuesday evening, I think it's perfectly fine with a little bit of self-promotion, isn't it? It is, right? So if you want to know more about behavioral code analysis in general, these techniques and some technical analysis, then you could probably do worse than checking out my new book, Your Code is Crime Scene, which just came out in a second edition last week. So with that covered, I'll be hanging around for the rest of the conference. I'll be super happy to continue the conversations during the party. And I want to thank you for showing up at this session. I hope you enjoyed it, and may the code be with you. Thank you.